All right, so here's where we left off, and it's molecular geometry. And we've been through this a bunch of times in class, but let's just go through it real quickly here. So it helps us sort of visualize what shape covalently bonded atoms become as molecules. And what you're going to do is whatever element is listed first, you're going to put that in the middle and surround it with the other atoms. The only exception is hydrogen is never going to be in the middle, so don't put that in the middle. If it is listed first, just go to the next atom listed. You're going to want to connect the dots, la 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 la, of the unpaired electrons. So anything that's paired is already kind of happy. It's got a buddy. The ones that are unpaired after you do your Lewis structures want to find another electron from a different atom to pair with, and that pairing will cause bonds. So you connect those dots, those are your bonds. You tidy up, kind of move those bonds around so that it looks a little neater, and you can determine your geometry using the Vesper chart. And also you want to determine if there's a polar bond present, which you use electronegativities. So to determine the geometry of a molecule, you're going to want to just base it on the number of elements attached to the central atom. If there are two atoms attached to a central atom, it could be one of two things. It could be linear, which is a situation like carbon dioxide, two atoms bonded to a central atom that is all lying in a line, so that's linear. And then bent is an example of water. So you have three atoms here, a central atom with two atoms bonded to it. And because of these lone pair, you get more of a bent shape than that linear shape. If you have three atoms attached to the central atom, it could be trigonal planar, which is this shape, where it's sort of like a triangle, but it would all sit flat on a desk. Or it could be trigonal pyramidal, where because of this lone pair pushing down on everything, you're going to have a little bit of a raised situation in the middle where these lone pair is pushing down these bonds. And so that's why you would have more of a pyramid structure. So trigonal pyramidal. And if you have four things connected to the central atom, that's always tetrahedral, like that. And I'd made some balloon animals in class, not really animals. And that was to help you visualize the fact that electrons need space from each other. They repel each other. The reason you can have a pair here and a pair in a bond is because they're spinning in different directions. But the bonding pair or the lone pair, they're going to repel each other, and they're going to want as much space as possible. And when you put something in a confined area and they want as much space as possible, it's kind of like putting balloons together at the nubs there. So your oxygen would sort of be in the middle of all these balloons, and the hydrogen would be coming out, one going back into the end of this balloon and one coming out of the screen here. And you can see that's more of a bent shape, and that's because these lone pair are pushing those bonds down a little bit because they need space as well. All right, so there's the Vesper chart. You can use that if it helps you sort of visualize all this. And again, see when the lone pair come in, that's when the bent starts happening, and that's when the trigonal pyramid starts happening. All right, so then a summary of covalent bonding. Maybe you didn't notice, but anything in group 14, that one that starts with carbon, they have four valence electrons. They're going to need four more electrons to become an octet. And because of that, they're looking to make four bonds. Group 15, that is topped with nitrogen, they have five valence electrons, that whole group. They need three more to get an octet. 5 plus 3 is 8. So they're looking to make three bonds. Oxygen group 16, has 6 valence electrons. They need two more to get an octet, 6 plus 2 being 8. So they will look to make two bonds. Halogens group 17 have 7 valence electrons. They need one more electron to form an octet, 7 plus 1 being 8. So they will form one bond, as will hydrogen. Hydrogen has one electron. If it gets one more electron, it'll be like helium, so it's looking to make one bond. So these bonds that they make can be polar, which is when atoms pull unevenly on shared electrons in an overall direction, and it depends on the electronegativity of the atoms. So here's an example of chlorine and hydrogen forming a bond, the bond represented by these two scoops of ice cream, the two electrons in that bond. As you can see, the polar bear, the chlorine, is getting a lot more of this ice cream than the penguin. So even though they're quote unquote sharing these electrons, it's possible that the sharing is not very equal. And you use your electronegativities to determine who is getting more of them than the other. And as a result of this, you're going to have a little bit of a negative and positive charge here. We'll get into that a little bit later. Nonpolar bonds happen when everything's shared evenly. So here's a non-Arctic background where a boy is sharing something with this monkey. So here's one atom, here's another atom, and they're sharing them evenly. And you use these electronegativities to determine that. So if you subtract these from each other, so if like N was bonding with O, you would subtract 3 from 3.5 and you'd get a number. If N was bonding with F, you would subtract 3 from 4 and you get a number. And since 3 minus 4 is 1, and 3.5 minus, 4 minus 3 is 1, 3.5 minus 3 is 0.5, this bond, the NF bond, would be more polar than the NO bond. And as a little guideline, I made this up. So if the difference in electronegativity is between 0 and 0.3, we're going to call that nonpolar. If it's between 0.4 and 1.5, we're going to call that polar. And if it's 1.5 or above, we're going to call that ionic. And just keep in mind that I made these up somewhat arbitrarily. And it's sort of like if you look at this shading here, when does a shading turn from yellow to green and when does that green become blue? I'm trying to draw a line and saying it happens here at 0.3 and it happens here at 1.5 and it happens above 1.5. But understand this is not defined near as clearly as this, but you can use this as a guideline. And I'm going to